here I believe we proved, not we proved, we stated. So we observed that like in the if you have a bipartite graph, right, and you are talking about matching, and suppose there is a matching which saturates a set of vertices, like let's say X in the bipartite graph, then for every subset of the vertices of X, one can immediately see that its neighborhood must contain at least as many vertices, because each of these is saturated in the bipartite graph, means that it will have a unique neighbor, right, that you can say the other endpoint of the matching edge. Right? So each of them will be in the neighborhood of S, and therefore neighborhood of S should be at least as big as the S itself, right? Now this is true for every subset because every vertex is matched. But if there is no matching, it need not be true. We saw some example also. Right? But what is interesting is that if this is true for every subset in a bipartite graph, right? For one of the sides, let's say X, if you know that for every subset of X, we have this property, then you can also find a perfect matching, which is a matching which saturates X, not necessarily perfect. All the vertices of X are saturated, and this is more surprising, right? So the necessary condition is also sufficient. So that is what Hall's theorem states. So given a bipartite graph G, and which has the bipartition into sets X and Y, then if G has a matching that saturates X, if and only if for every subset S of X, the cardinality of the neighborhood of S is at least as big as the cardinality of S. Okay, so how do we prove this? So first part, necessity, we already saw that to saturate the vertices of X, we need to have edges, which form the matching, right? And therefore, each of these the edges will provide a unique vertex in the neighborhood of S, and therefore the condition is immediate, right? So n of S is greater than or equal to cardinality of S is clear. So what we need to prove is the sufficiency part, right? For the sufficiency part, we will assume that we have the graph, and for every subset of one of the partite sets X, we have this property that n of S is greater than or equal to S. Then we will assume, we will consider maximum matching in the graph, let's say M. And if M is saturating X, then there is nothing to prove, right? So every vertex is saturated. So if it is not, then we will actually show that the assumption that n of S is greater than or equal to S is false for some subset, and this is what we want to prove, right? So this is what we are aiming to prove. Okay, so here is a typical picture that you can look at of a bipartite graph, and we have a maximum matching which is denoted by the blue colored edges in this picture, and we will assume that one of the vertices in X is not saturated, at least one, right? There could be many, but let us say that some vertex U belonging to X is not saturated. So our aim is to prove that we need to find a subset of X such that it violates the condition. Then we are done, right? So take any arbitrary graph, right, and find a maximum matching in bipartite graph. Find a maximum matching, and take some vertex which is not saturated. Then we will be able to find a subset of X whose neighborhood is strictly less than the cardinality of X. So to prove this, we start with one of these vertices which is not saturated, let's say U. So starting from U, you look at all possible M alternating paths, which starts at U, right? So M alternating path is that the edges will alternate between the vertices. I mean, the edges alternate between the edges in M and which is not in M, right? So I can start with an edge which is not in M, right? By itself, it is an M alternating path. Right? So from U to some vertex you go, that is definitely an M alternating path, right? So you look at all possible M alternating paths starting from U. Right, so for example, I can go from U to this vertex. Then if there is an edge of M which is incident with it, I can just go right to the other vertex, and then I can again continue by taking some vertex which is not in M. Then I can continue if there is an edge which is in M, right? But now I cannot come back here because of course it is coming to an already visited vertex which is not a path, right? But this is the idea, right? So you start from a vertex U, then take the edges not in M and then edges in M in alternate ways, so that you look at these vertices that you have, right? Now all the vertices which are part of the set Y, right, that you can reach by M alternating path from U, right? I will collect all such vertices and call it as a set T. Okay? So the set T of vertices is the set of vertices, which is reachable from U by M alternating paths. Okay? So for example, you can see that T is these three vertices in this graph, because I can go from U to this middle vertex. Then I can go from this middle vertex, take the matching edge, blue edge, to up vertex, upside vertex. And from there I can go back to the first vertex here, right? Similarly, I can go from U to this middle vertex, go here, and then take this edge to reach here, which is also an M alternating, right? Now, any other vertex, right? I cannot find an M alternating path, because if I go from U to these vertices, I cannot of course pick an edge which is not in M to go from Y to X. So I have to reach some vertex of S and then to X and then come back to here, right? Which is not there. So therefore we can see that only these three vertices are reachable from U by M alternating paths. Then I define a set set of vertices in X which are reachable by M alternating paths, right? So these are the vertices which I have noted in S, because U is always reachable from U. Then from U I can go to the middle vertex, then go back by taking a blue edge to this vertex, right? So therefore this is going to be in S. Then I can go from here to here, and then again go back to reach the first vertex here, which is second vertex in X, which is S, which belongs to S. And similarly, I can go to this vertex, come here, come back here, and go to the vertex in X. Right. So pick all such vertices and call that subset as S. Okay. So I have now defined two subsets, right? Subset T of Y, which are reachable from U by M alternating path, and the subset S of X, which are reachable from U by again M alternating. Now, we claim that the cardinality of T, right? Cardinality of T is less than or equal to cardinality of S minus the vertex U. Okay. So cardinality of T is less than or equal to cardinality of S minus the single vertex U. And why is this? Because every time I reach a vertex in T, if T is not saturated, that vertex is not saturated, then the path that we have defined, right, is an M augmenting path, right? Because an M alternating path where the starting vertex and the ending vertex is not saturated is an M augmenting path. If it is an augmenting path, we already proved that there is a matching which is larger, right? We started with a maximum matching, right? M is the maximum matching, and therefore you cannot have any M augmenting path in the graph, right? So therefore the finishing vertex must be saturated vertex. So therefore the vertices in T are saturated. So every time I reach a vertex in T, I should be able to take a blue edge to continue the journey, right? Because once I reach here, there is a blue edge which I have not used, and then I am going to take that edge and extend my alternating path to S. So therefore, corresponding to every vertex in T, I have some vertex in S minus U. Therefore, cardinality of T is less than or equal to cardinality of S minus U. Now, on the other hand, I also say that cardinality of T is greater than or equal to cardinality of S minus U. And why is that? Because every time I want to reach a vertex in S, right? Now by taking an M alternating path, I should start from U, reach some vertex, right? And then take a unique edge from T to reach S, right? So of course, other than the vertex U, if I am looking at S minus U, every vertex is reached by a matching edge, right? So therefore, these matching edges, I cannot have two blue edges incident to one of the vertices in T, right? So therefore, each of these vertex is uniquely matched with a vertex of T. So therefore, and because we can extend, right? Anytime you reach to a vertex in T, we already noted that you can always extend it. So therefore, you should have a vertex in S minus U corresponding to every vertex in T. And because of this, cardinality of T is at least cardinality of S minus U, which says that T and S are in one-to-one correspondence, right? So we have two sets T and S minus U which are in bijection. Okay. So what does this tell us? This tells us we have the set of vertices reachable from U by M alternating paths, and set of vertices other than U in X which are reachable by M alternating paths are in one-to-one correspondence. Now let us look at the neighborhood of the set S, right? Look at all the neighbors of S. Now I claim that the only neighbors of S are the vertices in T, right? It cannot have any vertex outside T as a neighbor. And why is that? Suppose there is some other neighbor, right? Suppose there is some other neighbor. Right? If there is a neighbor, like this, right, which is the outside T in what? He would have had a bigger maximum matching. No. So suppose there is an edge from S to some vertex in Y other than T, right? And if this vertex is already matched, then this is one of the vertices which are now reachable from U by an M alternating path, because every time I reach S, I am actually reaching there by taking a blue edge, right, the matching edge. And since I am reaching there by a matching edge, right, because it's a bipartite graph, every time we switch the sides, we are basically switching the type of edges also, right? So every time I am going to T, I am taking an unsaturated, an edge which is not in M, and whenever I am going to S, I am taking an edge which is in M, right? So therefore, this edge which is there, I have added, is an edge which is not in M. So therefore, if I reach S and then take an edge like this, I can actually extend the M alternating path to reach this vertex also, which means that my T would have included this also, right? So therefore, if there is a vertex outside T, which is incident to a matching vertex, then of course we know that our T was larger, right? And consecutively S was also different, right? So therefore this could not be the case, right? Now on the other hand, if this edge was to a vertex which is not saturated, that is also possible, right? Why can have vertices which are not saturated? Now, if this is not saturated, then this path becomes an M augmenting, right? Because I was taking alternating path, and this edge is reaching a vertex which is not saturated. I started from a vertex which is not saturated, and this in this particular case, as someone just mentioned, we get a larger matching because we have an M augmented path, right? So this is also not possible. So which means that the only neighbors of S is going to be the vertices in T. Okay, so if this is the case, well, so we already have proved, we have already have obtained the set that we were looking for, right? If you look at the set S, the S minus U has a matching with T. Therefore, the cardinality of S is strictly greater than cardinality of T, right? Including the vertex U, it has one more vertex in S. And this says that we already found a subset that we are looking for, which contradicts the assumption that n of s is greater than or equal to s, right? The cardinality of n of s is greater than or equal to s. And this is the proof. Okay. So again, I have written down here the proof. So to just repeat, you start from an unsaturated vertex, right? And define your subsets of x and y as s and t, which are reachable from u by m alternating paths. Because the graph is bipartite, every m alternating path from u must reach the edges, the vertices of y, using the edges that are not part of it, right? Because graph is bipartite. And because of this, anytime that you reach a vertex here, if it is unsaturated, we have an M augmenting path. Therefore, it must be saturated, and therefore, it extends to the vertices in X, right? And we define those vertices which can be reached by M alternating path as S, right? Those vertices belonging to S as to X as the set S. Then we show that the cardinality of S minus U is actually equal to cardinality of T, that there is a one-to-one correspondence between the vertices in T and S minus U, right? These are basically the matching edges. This is provided by the matching edges. And then we, once we show this, we can observe that cardinality of T and cardinality of S minus U are the same, and this tells that the neighborhood of S is essentially contained in in T, and this gives a contradiction because S has more vertices than S minus. S has more vertices than T, and therefore the neighborhood of S is strictly smaller than the cardinality of S. And that's it. So this is precisely the proof. Okay. If any questions, of course, you can ask. Otherwise, here some homework questions for you. So the first question is to consider a graph in which some subset of vertices is saturated by some matching. Now show that this set is also saturated by some maximum matching of the graph. This should be quite easy. Then there is another question that you have two persons, Alice and Bob, and they want to play a game on graphs. Okay, so they take some arbitrary graph and then start some game. Okay, so the game is as follows. So each person alternately select vertices Okay, so the first person picks vertex v1, second person picks v2, then v3 by the second first person again, v4, etc. But the condition is that every time you pick a new vertex, it should be basically extending a path, right? So v1, if you pick, v2 must be picked by, so that v1 v2 is an edge. Then v3 must be picked that v1 v2 v3 is a path, right? And similarly, we want to keep on extending this path. So the last person who is able to do this extension, right, choose a vertex so that you still form a path, wins the game. Okay, that is the game. Okay, so the game is that you keep on picking vertices which forms a path, and the last person who is able to pick a vertex which still forms a path wins the game. Now what we need to show is that if the graph has a perfect matching, then the second player has a winning strategy, and if the graph has no perfect matching, then the first player has a winning strategy. Okay. So here are the questions. To prove that the second player has a winning strategy, if he has a perfect matching, and show that if he has no perfect matching, then the player who makes the first move has a winning strategy. So what is the winning strategy? That you have you have a way to choose the vertices, right? So that no matter what the other person picks, right? You still be able to finish the game, right? So that, by picking the last vertex, which will give you a path. So this is what the question is. And here is another question. So you have a company. This company advertised n jobs, okay, for some positive integer n. It has advertised n jobs, and after their the period is over, they found out that there are n candidates who have applied the same number of jobs, but they found out that for some positive integer k, right, each candidate is suitable for a set of k jobs. Okay, so each candidate they found out that is suited for a set of k jobs, and each job has a set of k candidates which are qualified for it. And this is kind of surprising for them. But now the thing is that you can prove that if this happens, then the company can find candidates suitable for each job. Right? So they can fill the vacancy, finding candidates for each job. And so this is what you can show. Okay, so that is about our matching questions. Now here is another interesting thing, which is called vertex covers. So we have looked at several covers so far. Now here's another cover, which is vertex cover. So vertex cover is actually a cover for the edges. That we want to pick all the edges by picking at least one of the endpoints. Okay? So you need to basically figure out a set of vertices, which is incident to all the edges. So a subset of vertices which is incident to all the edges. So in this case, for example, if I pick this vertex, and this vertex, then you can see that every edge is incident to one of these three vertices. Okay? Every edge is incident to one of these vertices. So if I remove these three vertices, you will get an empty graph, right? So this tells something, right? If you define a vertex cover, what would be the complement of the vertex cover? So if you have a vertex cover, what will be its complement? Anyone has any comments or ideas? Yes. So the complement will be an independent set, right? Because once you remove these vertices, you cannot have any edges in the graph, right? Because that's what we said, right? If you remove the the vertices, each vertex is, each edge is incident to one of these vertices. So if you remove that, what you get must be an independent set, right? You cannot have any other edges. So the complement of a vertex cover is going to be an independent set. But if you look at any independent set, its complement will also be a vertex cover. This is also an interesting observation, right? So if you take any vertex cover, its complement is an independent set. If you take any independent set in a graph, its complement is necessarily a vertex cover. Okay, so formally, a vertex cover of a graph is a subset of vertices such that every edge has at least one endpoint in it, right? And the vertices in S basically cover the edges of the graph. Again, another example. So the blue vertices here form a vertex cover, and you can see that the complement vertices must form an independent set. Right? This. Another example here, you see there are two vertex covers that complement to each other, right? The vertex cover in blue is not only a cover; it's also an independent set, and its complement is again, we know that it must be an independent set, and it is also a cover in this case. It's not the case always, right? So here we have a graph where we have a vertex cover, and its complement is also a vertex cover, and therefore both of them are also independent sets. We can have different cardinalities for the vertex covers, right? We can have different graphs where there are several covers, and each of the cover may be of different cardinality. So here is an example where very simple example where we have a cover of size 1 and a cover of size 3, right? So if you don't pick the middle vertex, you have to pick all the other vertices. You find a vertex cover of minimum size. So the minimum vertex cover is the smallest cardinality vertex cover, and we denote it by small tau of G. Okay? So the Greek letter tau of G denotes the vertex cover, minimum vertex cover number. And again, in the book by Douglas West, I think they use a different notation. It's okay. You can follow this one for the time being. Anyway, we will make it clear what notation we are using if you are using a different notation in the exam. The use of the vertex covers. So for example, here is an application, right? So let us say that the city of Chandigarh in India, right? This was a planned city. It was not a city or earlier they basically built up the entire infrastructure there, starting from the scratch. So unlike most of the Indian cities. Right? So the advantage is that the most of the roads are straight lanes. One can look at the map of Chandigarh and see that is indeed the case. So you have a city where all the roads are straight lanes, and now what they want to do is that they want to increase, let us say, the security by installing. Please mute your mic unless you are asking questions. So, what I was saying, yeah. So we have, the city of Chandigarh, where you want to install, CCTV cameras, let's say, to increase the security. Now, because the roads are straight lanes, if you have an intersection as a junction, And at the junction, if you keep a good camera which can cover all the sides, then this can basically cover all the roads. So at least we will assume that it is the case. And now the question for the government is to find the minimum number of cameras, because that will reduce the cost of interaction, right? So for that purpose, they want to find out the smallest number of cameras which will do the job. And of course, we know that since the traffic network, the edges are represented by the the roads are represented by the edges. If you find a vertex cover, right, we know that it will cover all the edges, right, by definition of the vertex cover. And if you find a minimum vertex cover, it will tell you the minimum number of cameras required. And here is just a nice application I just mentioned. Of course, there are many other applications. I'm not going to any of these. Now we define what is called an edge cover. So an edge cover of a graph is basically a set of edges that covers all the vertices. That basically the edges that every if you pick these edges, then the vertices must be all incident to one of the endpoints. And we denote by rho of G the number of minimum size edge cover in the graph. So here is a graph, and there is an edge cover which is colored in the yellow colors, right? So these three edges will cover all the vertices, and then we have a nice edge cover, right? Then on the other hand, if you take this graph, right, then you need to include all the edges, right? In this graph, you need to include all the edges to cover all the vertices. There is no escaping that. So what are the different numbers, parameters that we have studied in this case? That we have a graph G, then we define what is the maximum independent set, and the cardinality is the denoted by alpha of G, the independence number. Then that was some time back, right? Then we defined the maximum matching in a graph, and its cardinality is denoted by nu of G. Then we define the vertex cover, right? Tau, and is the minimum cardinality vertex cover, and rho is the number of edges that will be in a minimum edge cover in the graph, right? So these four parameters are there. Now one question that I want you to think about is to find some relations between these parameters. What you can find. So again, I think I already mentioned this. So given a graph G, and if you have a vertex cover, then its complement is an independent set, right? So we already mentioned this. So now you can formally write, why it must be an independent set if you want. And the homework questions will ask you to find these relations and show the relations. So given a graph G, then show that the maximum matching number and the edge cover number, right? They sum to the number of vertices in the graph. Then the second question asks you to show that the maximum independent set number plus the vertex cover number, they must also be equal to n. This should be kind of pretty clear from what we discussed before. But the first question might be a little more trickier. Then you have the third question to show that if you have a maximum matching M, right, then the cardinality of the maximum matching is greater than or equal to no, maximal matching, not necessarily maximum, right? So any maximal matching should have at least half the number of edges in the maximum matching. Here is a nice graph, and you can try to find a perfect matching in this, or try to prove that it has no perfect matching. Right? To prove it has no perfect matching, you have to find some observation. It will be very easy, like in very, very short. But I don't know whether it will be very easy, but it will be nice to think about. Or you find a perfect match. Here is a question. If the graph G is bipartite, then show that the independence number is equal to the number of vertices by 2 if and only if G has a perfect matching. And one direction will be immediate. I think the other one is also not very difficult. Then sixth question is that if you have a vertex cover C and a maximum a matching M, then show that the vertex cover number is not vertex cover number. The cardinality of this vertex cover will be greater than or equal to the cardinality of the matching. So this is the relation between the matching and the vertex covers, right? So the vertex cover will always be greater than or equal to the matching number. And this is again very easy to see. Now, one can show that if the graph is actually bipartite, then the maximum matching number will be actually equal to the minimum vertex cover. And where this equality is obtained. For this thing, we are looking at the minimum vertex cover and the maximum matching. This will become an equality if the graph is bipartite. This is called the Egger-Koenig theorem. And this theorem can be proved if you have proved any of the following result, that is Hall's theorem or Menger's theorem. We have proved both of them. So proving this theorem from Hall's theorem or Menger's theorem will be very easy. So I want you to look at this as a question. Prove that for a bipartite graph, the maximum matching number is equal to the minimum vertex cover using Hall's theorem. Then the second question asks you to prove that the same thing using Menger's theorem directly, right? And then the third question asks you to prove Hall's theorem using this theorem again, which is also easy. So one can actually show that there are a set of like 7 or 8 theorems in combinatorics and graph theory, which are all kind of equivalent in the sense that if you prove one of them, proving the other from assuming this will be very easy. We will not go through all of them, but here are the 3 interesting ones related to us, our case. Okay, so I will give you some topic to read regarding this matching, because you can talk about the algorithm for finding maximum matchings and all, and it's kind of easy. In fact, we already know that if you find an augmenting path, then you can find a larger matching. And if the matching is not maximal, you always have an augmenting path, right? These two we already know. And using this, we can basically find an algorithm, right? You keep on finding augmenting paths, right? Start from any edge as a matching, right? Or any arbitrary matching, and then you just keep on doing this, right? Find augmenting paths, extend. Then take the new matching, find augmenting path, and extend. And if you repeat this enough times, you will always find a maximum match. So this can be a theorem to prove, right? So repeated application of the augmenting path algorithm will end up. So I want you to read the algorithm, right? See how it basically works, get an idea about this, and also try to use this to actually prove the theorem that you can find a maximum matching algorithm using the augmenting path algorithm. And if you have, what is the time? We have time. So if you have weighted graphs where the edges have some weights, then you can talk about weighted matching. You want to find a matching which not necessarily maximize the number of edges, but the weight of the edges, right? So you can ask for maximum weighted matching. And one of the algorithms for this is Hungarian algorithm, which is also mentioned in the book that you have. And I want you to take a look at this. It will be very nice to take a look at this. Probably I will not ask much about this topic in the exams, but it would definitely be useful if you read about this. So I suggest this as a reading topic. I want to now mention another name for the Hall's theorem is also called Hall's marriage theorem. In fact, the Hall's theorem is slightly more general than the marriage theorem. So, what is the marriage theorem? So, marriage theorem was actually, I forgot the name of the person who proved this, but much before Hall proved, there was this theorem which was actually shown that suppose you have a set of men and women, and they give their preferences for the partners, right? So each person, right, each man, makes a preference list for the the ladies, right? So who are all there, like whom I prefer the most, the second most, third most, etc., right? And similarly, women also make their preference list, right? So which man is more suited for me, etc., etc. So they make the preference list, and then suppose this information is given to you, right? So you have like equal number of men and women. They have these preferences. Now the question is that can you find a uh, you know find a partners so that you know the marriage is a stable marriage. So what do you mean by stable marriage? That suppose there are two persons, let's say X and Y, right? And and in a community, right? And then X has X finds that like there is a person so X and Y are not married, but X and Y, like say X is a man and Y is a woman, right? X and Y are married to some other, like X is married to somebody else, Y is married to somebody else. But X actually prefers Y to be his partner, and Y actually prefers X to be his partner compared to their own partners. So if something like this happens, of course, they can basically divorce and then get married together. Right? They'll be happier together. So if something like that happens, then the marriage may not be stable. So we say a matching is stable matching if for no pair of people, let's say P and Q, right? P prefers Q to his partner and Q prefers P to her partner, right? So if that does not happen, then the matching is a stable match. Now, in the previous example that we saw, right? So I claim that XA, YB, ZD, and WC is a stable match. Right? So let's say XA, YB, ZD, and WC, right? ZD, WC. So this is it's a stable match, right? Why is that? Because if you look at X and A is the most preferred for X, right? And and if you look at the woman Y, of course she prefers Z to X, but Z does not prefer her, more than the current partner, which is D, right? ZD. So therefore, they will not have any problem. Similarly, you can verify for other pairs also. This property is true, right? That this situation does not happen. So such a matching is called a stable matching. Now, how do you, I mean, like can you think of an algorithm to find a stable matching? So these two people, Gale and Shapley, they propose some algorithm. Okay, so I will present two versions of this algorithm. One, the first algorithm where the men proposes to women, and the second algorithm, women proposes to men. What I want you to think about is that which algorithm is suited for the happiness of women, and which algorithm is suited for the happiness of men. So these are the two algorithms. One is that each unmatched man proposes to the person highest on his list, who has not yet rejected him. Proposes to the woman highest in his list, who has not yet rejected him, right? So you propose to the first person, she might just reject, right? Saying that, okay, no. Now, then each woman gets, suppose in the, the running of the algorithm, right? If each woman gets exactly one proposal, of course, they know that, because the persons are proposing to their, the highest in the list, they cannot get anything better, right? So therefore, if you get only one proposal, you know that okay, that's it, right? We cannot get anything better. And if each one has this thing, right, then we can stop. But if that is not the case, if at least one woman has two proposals, then maybe she can either say to the best proposer or say maybe, right, somebody, I can get somebody else, right, later. That is possible. And the others also can be hopeful that if this girl rejects, maybe that guy might again propose to her, right? So therefore nothing happens if at least one woman gets two proposals, right, two or more proposals. So in that case what happens, so then the algorithm says that okay, the woman says maybe, right, will not reject, right, well, let me think about it, right, to the highest proposer in the list, and then all the others, right, she will reject, like the lower ranked candidate she will reject. So then algorithm again runs, right? So again the proposals will be sent, new proposals, and keep on doing this till each woman gets exactly one proposal, and then we will say, okay, this is the matching, and then stop. And the woman GSW algorithm, right, is basically the women does the proposals, and men again see if each man gets exactly one proposal, then they stop. Otherwise, they will say maybe, and then continue. So these are the the algorithms. Now each algorithm will definitely produce stable matches. Okay, this is something we can try to prove. So this will be a nice question to think about, why it should produce a stable matching. And then second question is, which one will make men happy and which one will make women happy. Okay. So think about this and get back to me. The homework question is basically the same that I mentioned, that show that both algorithms produce stable matchings, and then show that men are happiest under the male proposal algorithm and women are happiest under the women proposal algorithm. So which says that society settings are more favorable to men. Right? The social norms that we follow currently are kind of more favorable to men. And then okay, so I think